Welcome everyone. On today's seminar, we have a special guest, Javier de Lucas Lie from University of Warsaw. He will give us a talk celebrating 16 years since his PhD defense, and the talk is entitled Lie Systems, a 16-year retrospective on 132-year-old theory. Javi, the floor is yours.
Thank you. Well, today is gonna be a short day. It's just a kind of anniversary for me, and I just want to resume to describe a little bit what has happened during these 60 years from my PhD on this work on these systems, and to talk about the beginnings of the theory, the main researches, the works that have been done, many curiosities, directions of research, interesting results, what it can be done now. Yeah. So, as I said, it's going to be a kind of historical talk. It's not going to be a technical one. After I will try to explain the most important things, the most important results, and the philosophy of the theory. So, okay, let us see. Well, the outline of my talk is the following one. I will present the origins and classical foundations of the theory of these systems from Lie, Vessiot, Guldberg, Königsberger and all these people toward the end of the 19th century. Then I will talk what happened in Canada in the theorem at Centre Recherches Mathématiques of the University of Montreal, and how Winternitz made a revival of the theory that was almost forgotten after the initial development toward the end of the 19th century. Then I will talk about how the theory and the results given by Winternitz and his collaborators in the theorem invited to make a geometric approach to the theory. And this happened toward the year 2000, and this idea survived till now because they are very fruitful. And finally, I will talk what is going on now on Lie systems, and I will talk about what I've done on the topic with my collaborators, because I've written around 60 papers on the topic, more or less. I've done a lot of things. I think that every topic that it's possible to do, it has been done so far. So, yes, as a curiosity, this is me. This is maybe my first day at IMPAN. It was in 2007, 2 years before getting my PhD. This is probably my first weekend in Poland. Okay, it was something like June 2007, while working with Grabowski on Lie systems. It was the time when Janusz and Carinena and Marmo made an important development of the theory, and I used this to start to make my PhD. Okay, let us start. Yes, allow me to recall you what is a Lie system, what is a superposition rule, although probably most of you know. Okay, so consider a first order differential equations that is normal form. That means that that the differential of the solution, the derivative of the solutions, can be written as a function of the independent variable and the dependent variable x. Yeah, and for these kinds of systems, and only for these kinds of systems, okay, we say that this system is a Lie system, is a meta superposition rule, and that means that there exists some functions and function independent of the explicitly independent of the independent variable t, such that when you have a finite family of particular solutions, generic finite family of M solutions, and you have a number of constants that is equal to the dimension of the manifold where the problem is defined, you can generate the general solution of the system. There are lots of technicalities about this. Okay, it's you can talk that you can try to describe what does mean generic family of solutions. Okay, you can say that this superposition does not generate every solution, but you can always generate solutions in open subset of the manifold. Yeah, and these five defines are that you can map. You can recover all solutions locally by obtaining one of these things on each open of the manifold. Well, there are a lot of technicalities about this, and there are lots of theories. Now, for example, with shapes or other new approaches to describe this superposition rule thing. Okay, but the main idea is just that you can generate almost every solution of UFS of the differential equation in terms of finite family and some constants. That the number of constants is determined by the dimension of the manifold. So the typical example is when you have, for example, linear, first of all, the differential system of differential equations, yeah. And by means of this, you can study lots of differential equations. You can study Ricard equations, you can study Mill-Levin equations, you can study Markov system, harmonic oscillators. There are lots and lots of systems. The problem is that this is very special. Most of differential equations are not this type. Most differential equations are not in normal form. Even in normal form, most differential equations are not this. Anyhow, it turns out this system appears in many important applications, and it's far more than enough to study the properties from a physical point of view, and also it is important because it's related to very important mathematical topics. So let us say that it's fully justified. So let me talk a little bit about the main result of the whole theory of Lie systems. And the main result was discovered by Lie on a result written with the help of Cephas. We edited the result in 1893. And what it says that Lie-Cephas theorem is that when we have first of the system differential equation that is non-autonomous, we can characterize these systems that admit a superposition rule, and they are the systems. The idea is the right-hand side, this thing here, for every t is just a vector field, what we call a t dependent vector field. That it means that you just have t-parameter family of vector fields in this. Okay, and you can say that one differential equation, one system, non-autonomous system differential equation of this manner can be proved to be a Lie system if you can write it in this manner. I mean, if the time-dependent vector field is a linear combination with certain time-dependent functions of a family of vector fields spanning a Lie algebra. Yeah? And x1, xr, well, not only span, but there are bases of the finite-dimensional Lie algebra. This Lie algebra of vector fields is called the Vessiot-Guldberg Lie algebra. Okay? And the geometric idea is that we can study Lie systems as curves in a Lie algebra. You see, for every t, this is an element of the Lie algebra of vector fields. So this time-dependent vector field is nothing but a curve in a Lie algebra, finite-dimensional Lie algebra of vector fields. Geometrically, this finite-dimensional Lie algebra can be integrated to give a Lie group action, at least locally. And it turns out that the Lie systems, okay, the solutions of the Lie system, the solution of this first of the system differential equations, they will be certain curves that live in the orbits of this equation. So this is the main idea. There are lots of things, lots of stuff about this thing, technicalities and things to study. For example, I could tell you that I have a word lately saying that this is not exactly true. Okay, there are systems where this dimensional, this Lie algebra is infinite dimensional. This is one of the things. And there are works in which we are trying to characterize this when this is not in normal form, because nothing is done about that. And it's an interesting topic that has been open for centuries now. Well, for 130 32 years now, yep, more or less. And okay, so we know what is it, this thing. And let me tell you how this appeared. So the first result of the first comment about superposition rules, well, they are a little bit lost. I mean, some people say that during a talk, Abel commented on these superposition rules. But the thing is, some guy in our work wrote that Abel during a talk made this comment. We cannot be sure about that. Okay? It's the only thing I could find is a lost word where someone said, Abel talk about it. This is the only thing. Then there are a lot of, in words, 1885, 1893, the idea of the Lie system was around. Lie was developing his theory of Lie group actions, Lie groups, the algebras to study differential equations, generalized and Vessiot theory for polynomials. To say, for example, that with differential equations, you can relate some parametric group, which allows you to describe when the system is integrable now. Like it happens with in Galois theory for polynomials. Okay, during that time, there was several people, for example, Königsberg, Vessiot, Guldberg, who were interested in describing how which system differential equations on the real line satisfy that the general solution is a third-time combination, third-time fraction of a feminine family of particular solutions and constants. Yeah, they have superposition rule. They were thinking that this occurs for linear systems of differential equations, for a finite something like that, and they were wondering which is the most general case where this happens. So for several years, I don't remember, I think it was 8-10 years, they were making more and more general results about the case on the real line, till Lie noticed what they were doing. And once he noticed, he said that this is, well, he was not very nice, but more or less what he said in a paper published after one of these papers by Vessiot, Guldberg, put his very something like, everything that was published a little moment ago, everything is trivial, it's just a result of my theory. I will write a theorem to say that what you have done is unnecessary and it's much more general, much more interesting. And this is what Lie did in 1893 to write the Lie theorem. But the general idea was written a little bit before that. So, I mean, the key concept what I said before, that every system is a cube, and I think dimensional algebra, but this is the main idea. So the thing is that Vessiot was ashamed, was criticized very hardly by Lie in it. So Vessiot said, okay, Mr. Lie has, Professor Lie is right, this is true, his role is true, so let us call these systems Lie systems because it's Lie's idea how they have to be done. Let us keep on working on them. So Vessiot did a lot about Lie systems, many approaches to study Lie systems by means of Lie group actions and several generalizations of Riccati equations with words that were almost forgotten. Indeed, I must confess that several of the things I did were partially done by Vessiot, but I noticed after publishing, fortunately, I always did more than he, but well, let's just say that it was a little bit problematic. So Vessiot did a lot of things, and that's why sometimes people call the system Lebesgue system. Okay? Well, there are certain results at the very beginning, studying reductions by symmetry, examples on R2 about these systems. They were ideas to generalize Riccati equations to R2, R3, or to higher order differential equations and things like that. And all happened mainly because Vessiot was working on the topic. Yeah? Lie mainly gave his theorem, but his theorem was the door to obtain many things. For example, Lie had a nice classification of finite dimensional algebras on R and R2, on C on C2 also. On C3, he said, okay, the problem can't be solved, but it's too long, it's trivial, or you only have to make calculations. But so far, so good. No one knows where these calculations are, so only a couple of examples are done. But by means of this, you can find many, many things. Yeah. So geometrically, as I said, a Lie system affects all the differential equations in normal form. It's a time-dependent vector field, and the Lie system is just a linear combination with time-dependent functions, a family of vector fields generated in affinity-dimensional Lie algebra vector field. Yeah. And as I said, what it happens is that this causes that the evolution of the Lie system is within the orbitals of the Lie group action. And what Vessiot did was to see that the general solution of the Lie system can be obtained by means of a Lie system on a Lie group. Okay. And one of the any solution of the Lie system on a Lie group is a G of t. And if you act this on initial condition, okay, the action of this cube in the initial condition gives you the solution. So what Vessiot said is that you can obtain the solution of every Lie system by means of the solution of a Lie system on a Lie group, what is called an automorphic Lie system, where the time-dependent vector field related to it is right or left invariant, and the action of the group on the manifold. Okay. In such a manner that the fundamental vector field of the action they have the one dimension. So this is what Vessiot did. Okay, this is what I said. And the thing is, after Lie and Vessiot and Königsberg and Guldberg and a couple of guys more, the topic disappeared. Almost no one was interested on it. Yeah. For something like it was 1993 till the 1970s, 1980s, okay, the problem absolutely disappears. There are works by Vessiot in 1903, 1905, until 7, I think. So for something like 70 years, more or less, 70, 80 years, everything disappeared. And then this guy appeared. This guy is Pavel Winternitz. I decided to put that a picture of him, very, very young. Okay. This guy is a legend in integrable systems. Right? In reality, he wrote a thesis about nuclear physics. I think it was about nuclear physics. I wrote a book that it was called the Bible. Okay. He did several oscillators in the fine theorem oscillator application in physics, the Smorodinsky-Winternitz oscillators. Okay, and there are a lot of people working on them now. It's something like he developed a couple of things, a couple of topics, and each topic on its own, it was strong enough to motivate the research of many, many, many people. Yeah. So Winternitz was born in the Czech, in Prague, I think. I probably remember. But PhD did it, I think, in Russia. Okay. And after several political problems, okay, he moved to the Syria in Montreal. I think it was in 1968. It was the invasion of the Czech Republic by the Russians. So at that time, if I'm not wrong, he moved to the Syria and he developed there his research group, which turned out to be one of the main ones of the whole Syria. Yeah, there were lots of people working with him. He attracted a lot of people all around the world to the Syria, to Montreal, and people started working on this topic. So this is the Syria, okay? And it turned out that there were lots of things to do. Winternitz was interested not only on the list systems as integrable systems, but also in Lie algebras, in Lie groups, and all the structure about that. And he was a specialist in classifying things and looking for applications. So there are lots and lots of applications of Lie systems, many, many, many fields. I mean, Lie systems were developed for differential equations, but Winternitz found that if the Vessiot-Guldberg Lie algebra is a particular kind, the so-called primitive transitive Lie algebras, over the complex numbers, you can classify all of them. There are several theorems developed by Snyder with Winternitz, two main works, and all the ones that came afterwards. And he was able to give canonical forms for the Lie system related to this Lie algebra vector fields. So it was a huge work indeed, and Lie systems appear as something that was always close to integrable systems. Yeah, and it had a lot of potential. Yeah. So the thing is, she essentially classified the most important Lie systems, yeah, those related to committed transitive Lie algebra. Essentially, most Lie systems can be reduced to them, okay, most important problems. The other thing is that this was done over the complex numbers. If you done over the reals, it's fun because Winternitz wrote a paper saying that everything is done. There is just a couple of cases that they are difficult, but it turned out that he was never able to solve these two cases. So far, they are still open, and no one so far has been able to classify them. Yeah? Most of the classification of these Lie systems for primitive transitive Lie algebras were done by means of very tricky, nice, and original constructions, yeah, to write the proper forms. But the problem is that for these real cases, there are no tricky manners to deal with them. So they are still open, yeah. And the thing is, Pavel and his collaborators started studying many topics related to these Lie systems, or Lie systems, they are also called. And they generalized them to many realms. For example, there are generalizations of Lie systems to deal with super differential equations. We can have supersymmetric systems related to Lie systems. As I said, there are also generalizations to deal with partial differential equations. Pavel, at a certain moment, decided that it's the time to move to discrete systems because they were, at the time, very, very interesting. There were financial support for studying them. And started discrete Lie system, discrete analogous to superposition rule. He found that high-level properties could be somehow translated to discrete systems, yeah, and did lots of results. The only thing is that his insights are very physically motivated. They are done just to focus on particular physical problems, and he classifies also things, but he doesn't look for a nice mathematical theory. The two things he does is he applies Lie systems to physical systems with important applications, or as a piece try to pick a classification problem and try to solve it somehow without a nice theory with nice definitions why needed. It just let's go for the final result somehow. Yeah. And there are lots of papers by Winternitz. He also started collaborating with many people from the theorem, for example, Herranz, Snyder, Grundland, many other people also from abroad. Yeah, very good people. And for many years, he started to think. At a certain moment, he moved to discrete systems, and he lost his interest on the topic. Some of his collaborators continued working on it. For example, Grundland, yeah, till the very present, continues the topic. But more Winternitz just moved to another topics. But at the same time, it turned out that Lie systems appear in other fields, for example, in control theory, where there are lots of bracket systems that can be described by means of them. Indeed, control theory is something is a field where this appears very frequently. And let us say that this Winternitz era is characterized by Winternitz model. And it's just that every Lie systems lie in the heart of every integrable problem. And what he used to tell me is that if you have an integrable system, somehow there is some Lie system related to it. No matter if this is a partial differential equation or a differential equation, whatever, there is a manner to relate that. It's not a theorem, yeah, it's just an idea that you can find them. So it's something that he said several times. So there are certain things about control systems, yeah, that's it's worth to say. And do you remember, for sure you remember that in the control system you have that the Lie system is a combination with time-dependent fields, with time functions. So in control systems, these functions, they are, for example, some control functions. It's something that you can choose. You can just put somehow to verify some conditions. Yeah? For example, you can try to find the time-dependent functions, I don't know, to go from point A to point B in a manifold by means of integral cube of one Lie system. Yeah. So you can try to minimize the time. You can put some function and try that it will be a Stremon on solutions. There are lots of things. Yeah. So in control systems, this is the idea. Is somehow you have to deal with these parametric these functions, and you have to choose them. The thing is that this way of studying Lie systems is pretty much open. I mean, there is a lot of things about geometric stuff for Lie systems, but it's not done what it happens for particular time-dependent functions. So it's something that it is worth it. It can be studied. Well, in certain cases, we proved that requiring something on these time-dependent functions, you can ensure integrability or different properties. Another thing is that the Vessiot-Guldberg Lie algebra, the manifold and number of solutions are related between them. This is something that found Lie. And he found in particular that the dimension of the Lie algebra is always smaller or equal or bigger than the dimension of the manifold times the number of particular solutions. So it says that if the Vessiot-Guldberg Lie algebra is big, the number of particular solutions tend to be bigger. If the Lie algebra is smaller, then the number of particular solutions normally is smaller. And it also tells there are other results that say if the Lie algebra is, for example, solvable, you can integrate the Lie system up to quadratures and things like that. It's more or less the equivalent of Galois theory, but for Lie systems. The Lie group, the Lie algebra, the Vessiot-Guldberg Lie algebra and the Lie group allows you to study the properties integrability problem of the problem under study. And all the geometry can also be used to study controlled system. Okay, for example, for Lie algebras, a system is controllable. I mean, you can, by means of a Lie system, okay, you can join points on a manifold if the Vessiot-Guldberg Lie algebra you have satisfied that the vector field generates the tangent space to the manifold, or well, there are other things similar to that. So, okay, as I tell, they were generalizations of the Lie systems, and one of these generalizations were for PDEs. Then the original idea for superposition rules, it was for ordinary differential equations, but in the same manner, you can try to study partial differential equations in normal form. Okay, partial differential in normal form, they are rather a very, very special case of partial differential equation. Okay, partial differential equation in normal form, I recall that is that the derivatives of the coordinates of the solution in terms of the independent variables can be written as a function of the dependent and independent variables. Okay, and there are these systems, the PDEs are the systems, if each partial derivative of in terms of one of the independent variables is a linear combination with function independent of the independent variables of a family of vector fields spanning infinite dimensional Lie algebra vector fields. So this seems to be quite specific. It is quite specific, but anyhow, it still has lots of application. And these systems were studied by Grundland on Odzijewicz. If I don't remember, I think that it was in 1990. Okay, so there are several theories about these PDEs, but if one wants to study this in full geometrically with all the details, one has to go to 2007, where Carinena, Marmo, and Grabowski developed the geometrical stuff describing the system. Indeed, the picture I saw you for the first time at the beginning of the talk, myself, was in 2007 and was when Grabowski, Marmo, and Carinena noticed how this has to be done. Yeah? And this is what they gave me. My first talk with Grabowski was about that. So this is one of the ideas. Another idea is that Lie systems can be generalized to higher order differential equations just by reducing the order, adding new variables to put it into a first order differential equation and ensure that this is a Lie system. Okay. Main application of this PDE well, you can find them in some works by Winternitz. Look, you have to look for it. He will not say that it's a PDE Lie system because he wasn't interested in giving names, giving formalisms. He was interested in applications and getting results. So you have to read his work to find where these examples appear, yeah, or my thesis, PhD thesis, or my book with Sardon, because then you will find the reference. So most of these applications of these thinkers have been, well, we have a few of them, we have not many, but they reduce to Bechdel transformations. You can describe conditional symmetry, you have soliton equations, you have integral field models, and you have hydrodynamic equations, for example, describing fusion modes of plasma. Well, truly speaking, it seems that there is quite potential in this. You have Lax pairs. It turns out that the singularity structural Lax pair can be described more easily by means of systems, what PDE systems in this. So you have this thing that this is Thomas Sobczak PhD thesis topic, yeah. You can go this way. Okay. Let us say that after Winternitz and after what did happen with this result, after several years encouraged, for example, the world, the Syrian with Herranz, with Warsaw, encouraged that people will start things of this Lie systems geometrically, yeah, after the 2000s. And we come to the model theory, okay, to the geometric theory of Lie systems. It's what more or less it's done till 2000, the year 2000, 2009, that when I was writing my PhD. So the original work with all this stuff, okay, there is one book, Lie surface systems, a geometric approach, I think that is the title, by Carinena, Marmo, and Grabowski in the 2000. And there is the work in the 2007, I think it was, about the superposition. Yes, 2007, about superposition rules for Lie systems and partial differential equations. Well, several are done. Superposition rules, they are generalized in several ideas. The key idea, the key geometric idea is that superposition rules are reality horizontal connections above. Yeah, this is what they did. Yeah, and so by means of this, they managed to give a geometric approach to Lie systems, and this approach was afterwards used by, well, it was my idea after my PhD thesis, that it was to mix geometric structures with Lie systems. And this was done in a train from Warsaw to Kielce. Yeah, that I mixed both things, and at the very beginning, what is the point of this? Yes, what is the point of assuming that a third Lie system is such that is also a Hamiltonian one? I mean, the vector fields of the Vessiot Guldberg algebra, they are Hamiltonian. And it turned out that it had lots of applications. Yeah, indeed, I remember at the very beginning that was the point of all this. And it turned out that, well, many things appear. Lots and lots and lots of things. And this was the topic for several PhD dissertations, theories about Poisson coalgebra, many things. The main idea, the first thing we found, it was the so-called Lie Hamilton system. That was a short work done with Cristina Sardon in Carinena, okay, where we one of the first was done by Cristina with myself when I was his PhD supervisor, and it was about these systems. It was just taking a look about the properties and taking a look where they appear. Well, the thing is, the first word is just a description of the main definitions to be done, the main structures appearing. But if you start trying to figure out what is new, the formalist was new, several results were new, but some ideas were previously done. I mean, all this stuff was known by Winternitz. Okay, so the examples, for example, German-Bock equation or the Milne-Pini equation and things like that were done. Well, Winter knew about that, but he didn't want to make any formalism about it. And particular results that appear in the book by Grabowski, Marmo, and Carinena, they are even, I think that is Poisson algebra. No, I was B algebra approach, I think, about this thing, about superposition rule. Okay, the thing is that there were several results, but they almost had no applications. The application developed there turned out that they didn't give much things, and there was no real theory about it, so we did it. And after that, we found the example. The example is Riccati. It turned out that Riccati's equation with a superposition rule that it was known for ages, but the development, the description of the superposition rule was done by solving one of the methods, by solving a system of PDEs. It was the result of Carinena, Marmo's and Grabowski approach. And what we found is that when you obtain the superposition rule, the PDE can be related to certain vector fields that are Hamiltonian. And the Hamiltonian factor of these vector fields, they close a Lie algebra of functions. And this Lie algebra has a Casimir. And a certain representation, this Casimir, let's say this way, could allow you to obtain an integral a third time function, which gives you the superposition. So this was the thing that was very interesting. The Casimir of a Lie algebra by means of a representation and the Poisson structure allows you to obtain superposition rules immediately, easily, and geometrically. So this was the main idea, yeah? And this was done by means of Poisson coalgebras. I remember that it was in 2009, 2010, something like that I read the Poisson coalgebra method by Ragnisko, Herranz, Blasco, Ballesteros, all the people from Burgos and people from Rome working on it. And I noticed that, well, you can generalize this to time-dependent systems and you can use it. So we were there, we wrote the paper, and it was one of the most cited papers I had in my lab. It turned out that this idea was pretty good for obtaining the superposition rules. Yeah, you have Lie algebras, Casimir. Everything that is related to Lie algebras can be described, can be used to study these systems. Okay, Poisson coalgebras can be in Steinhoff, structure can be used. There was a nice relation between this and non-commutative geometry and Poisson coalgebra geometry to study superposition rules. There are many results that have not been studied. For example, the superposition rule, it's not been studied if somehow it's a symplectic of fields in a bundle. There are open problems, yeah, and there are things to do. But this is what it was done. The thing is, this theory was pretty much generalizable to many realms. So many people started to do it. I did it also myself a third time cases. At the third time moment, I decided that most of these things, they are exactly the same. So they are interesting, but you have always to find some idea to justify to use more structures. But the idea is you have a system, you have a Vessiot-Guldberg algebra, you require that this Vessiot-Guldberg algebra would be a algebra symmetry of a geometric structure, symplectic form, a Poisson B-vector, a Dirac structure, a Jacobi, a Riemannian metric, a symplectic structure, a contact structure, whatever you want. And then the Poisson coalgebra method can be generalized in many cases. And you can copy and paste and deal with more and more and more and more general things. And you can use Poisson coalgebra, you can use certain properties of this theory to study the integrability of this system. So you can go this way. It's always nice to find a new structure, but this normally is a little bit too repetitive. The main thing is that when you have Poisson, these Lie Hamiltonian systems, it turns out that there are 13 results that say that you cannot use this, never will be able to use a Poisson structure to describe a thermodynamical system as a Hamiltonian one. And Dirac, Jacobi, Riemannian, and other structures appear. And essentially, this is what tells you that this is nice. And the other thing about this is not about the generalization of Lie systems, the use of compatible geometric with Lie system. Rather, what I found is the other way around, that if you study K-symplectic geometry, Riemannian geometry, Jacobi geometry, and Dirac geometry, if you have Lie systems with compatible structure of this type, you will be able to find nice results about this. For example, there was at the time with Vilariño, we did a work about K-symplectic Lie system with Vessiot, Guldberg, Ibragimov, Hamiltonian vector fields with a K-symplectic structure. It turned out that there we obtain a certain bracket with functions, K functions, that was supposed that it was not useful. It was not, does not exist, or if it exists, it's not useful for nothing. And it turned out that it is nice, and there is nice result of K-symplectic geometry. So sometimes Lie systems allow you to develop this geometric style. This is the idea. Well, this is the most easiest case of K-symplectic one of these cases. That's can be described. That is not trivial. So K-symplectic Lie systems is just that every element, every basis element is of the basis of the Vessiot-Guldberg algebra is Hamiltonian with respect to several closed K-force whose intersection is trivial, and the contraction of every vector field with every of these elements is too close to forms that might be generated is the differential function. And these functions, you can, this is space of K functions because you say that for every vector field you will have K of them. You can define the algebraic structure. You can, you will be able to do it. Dirac-Jacobi Lie system is more or less the same. Jacobi is related to contact geometry, which has been recently studied with Xavier Ribas and other people. Thomas Sobchak with K contact geometry generalization. Well, this system appear, for example, to sparse derivative to study the sparse derivative application, for example, string theory, for the integrability of certain systems, it has certain application, well, these are 13 properties of this system.
Sorry, could you briefly mention what you mean by integrable system in that context?
Okay, so you can study in many manners, So let us say that Lie systems, Hamiltonian Lie system, could give to integrable systems in the usual stuff. I mean that you will have certain functions functionally independent on a 2N manifold, and of them that there will be an involution. That is the typical Liouville integrability. You will have necessarily this type. Indeed, this was the first idea. This was related to the idea with Marmo to generalize somehow this to so-called Fourier system, something like that. So you have things like that, or you have other systems where this integrability was not so strict commutative. You can use that it will be, for example, this integral motion will not be commutative. So the structure of the Liouville integrability is not true, and instead of Tori, you will have something different. Or you can talk about integrability in the sense that you will be able to integrate up to quadratures. All this stuff you can do now. Okay, so it's very general. It's difficult to give a specific idea because it can be applied to anything. Some of these things are developed Okay, you can find in the paper. Some of these things were not said, but they can be found. I mean, if you read the papers, you will find it. And it is clear now.
Yeah. Well, my question was more like because you were talking about Jacobi and these more general structures, and like
Okay,
in
yes.
Poisson, involutivity doesn't imply that Hamiltonian vector fields are tangent to the leaves of the foliation, neither vice versa in general. So.
In this case, it's a little bit more complicated, a little bit more technical. Okay, but for example, do you remember that you have a work doing the integrability for dissipative systems? Yeah, that integrability that the functions they are not involutive anymore. Yeah.
Mm-hmm. Well, they are involutive in the sense of Jacobi, but yeah, let's say that the integrals of manifolds are no longer level sets.
Yeah, I mean, in this way,
you
could do exactly the same with this.
Okay.
But I never did it. It's just
okay, so it's not done yet.
Yeah, well, yeah. It's. Okay. I mean, many of the things I'm telling you are things that it can be done, but I didn't. Yeah, that's I don't know. I was not interested enough to deal with them, but they can be done. Okay. So thank you for the question. So some important things in years 2009, 2020. In 2009 was when we started with the geometric approach to the system with Carinena, also with Sardon, with Cristina. Yeah. In 2011, they were quasi skins and Lie-Famish. They are generalizations of the systems, where the superposition rules, they are Lie systems that up to a third time transformation, Lie group transformation can be written as Lie systems. In 2015, they were Lie-Hamilton, hierarchy systems. There was a unified framework for them. And 2019, 2021, and afterwards, they were k-symplectic, multisymplectic, symplectic Lie systems, and things of the sort. That it was, well, in this last part, it was something that the initial theory was developed for ordinary differential equations, but it turned out that the structured area for field theories can be also used for ordinary differential equations. So the thing is, as I said, these systems can be used to study these modern differential structures, and these modern differential structures can be used to study these systems. So this is just several ideas about these systems that they give rise to Lie-Hamilton, Dirac, Jacobi systems, symplectic multisystems. It's a bit historical, yeah. Not the relation between these, they are different. Okay, so what is going on now? Yeah. Well, Campoamor-Stursberg, one of the things they have classification as the Lie algebra vector fields up to dimension 4. So yeah, somehow you can study all the system up to dimension 4. They were works by, I think it was Ibragimov, yeah, that were studying the canonical form for certain Lie algebras up to a certain dimension, certain manifolds. They were trying to look for canonical forms for Vessiot-Guldberg Lie algebras, or studying all Vessiot-Guldberg Lie algebras of particular manifolds. Yeah? I already said that for primitive transient Lie algebra was done over the complex for Winternitz. But there are many more cases, okay? The main ones were done by Winternitz, but that doesn't mean that they are other things. Campoamor did, Ibragimov, I think it was Ibragimov, did, and some of the collaborators. They are studying the Lie system on certain manifolds, contact manifolds of different types. And we were studying higher order differential equations, okay? Second order and higher order orders. This was for the Riccati hierarchy with Grundland. And well, we were paper interesting public as unit differential equation. That is one of the best ones. I mean, that is one of the first 20 in the unification report, like that. And they were interesting, yeah. Grundland, Odzijewicz, and myself, we were studying these PDEs. They are nice models. For example, there's the Witten, Zumino, Novikov, Witten, Zumino, Novikov. I don't remember the last name. Winter. I don't remember. There are models appearing. Winternitz, Zumino, Novikov systems. Well, you'll find it. A reduction of KDB, total conditional symmetries of this time can be studied by mistake. What we did lately is about multisymplectic, polysymplectic, contact manifolds. Of course, if you want to study multi-contact, you will be able to develop multi-contact systems. You can do, well, we did symplectic system. You can do co-contact system. You can do CACO. All these new geometric structures can be applied, and you will find examples. Most of that. I haven't checked them out, but it is possible. With Dili systems, K-symplectic, co-symplectic, and all this stuff, we have been studying reduction techniques that are related to them. And you can even find new ideas for reduction, for example, multisymplectic reduction when inspired by the reduction of Dili systems, multisymplectic systems. And now we have many other topics, many realms. For example, there was a night work by Ortega and my goodness, what is his name? It's Ortega and Lázaro about list systems that they are stochastic differential questions in the Statonowitz approach. Yeah. And they prove that a lot. They have lots of applications, for example, in models to study market prices. Yeah, they have application for epidemic models, for example, for coronavirus or things of the sort. Also for satellites or for different types of systems. They are in, for example, situations in which there are some chaotic behavior, yeah? And it turns out that many of the models that were studied exactly now, they can be made stochastic. Well, you have to apply all this stochastic stuff, new technical things appear that you have to fix. Several things, for example, the Poisson coalgebra method can be employed to them, yeah? And, there are lots of examples to be studied. As I say, we find coronavirus examples, market examples, many stuff. And indeed, they are roughly studied, yeah? There are other approaches to some quantum systems for infinite dimensional manifolds. We do it also a lot about it. It's quite difficult, it's quite technical, but at the very end, it turns out that you can define systems on infinite dimensional manifolds. You can study, for example, integrability on infinite dimensional Hilbert manifold. It's not done. I said, yes, it can be done in certain cases, interesting cases. And for example, I found that non-commutative geometry can be used to find symmetries of these quantum systems. That it can be done, but I didn't do it because I didn't want to enter this, but it is a potential way of doing this, of studying this. But you can add many stuff. You can do you can study super list systems on super manifolds. Winternitz did a couple of things on it, but truly speaking, he didn't make anything in a formal manner. So you will find superposition rule, as he said. He did several things. Everything is fine. Everything works with super Lie groups, super algebras, but there are no definition, no theory, global theories, no formalisms about anything. So, truly speaking, it is open. But the formalism is extremely non-trivial. Or it may happen that under appropriate assumptions, it's very easy. Yeah. There are examples of it. Yeah, they can be studied to motivate it. Well, maybe. I don't know. Yeah, I have several potential ideas, but I have no bloody idea. I know that I could write the theory. If I sit down, I start doing it, but I never did. Yeah, and the reason why I didn't, because I started notice that you have to integrate even super vector fields. There are ways to do it to all super vector fields, but you will have to use interpretations that no one fully knows where they come from. Yeah, that they work, but there is not a full justification of it, apart from the fact that they work. So, well, I don't know. Maybe someone wants to do it. maybe they will find certain applications. I find super oscillators of this type and other systems, quantum mechanical systems that can be studied, but I don't know how far one can go. Well, it's a possible thing. Well, there are also discrete systems. Christina Sardon was a little bit more interested than myself, but we wrote a paper a couple of years ago about the topic. You can use numerical methods, and there was Gabriel Pietrzkowski also proved that you can use certain methods to make numerical stuff, discrete stuff for the systems. Yeah. And as I said at the beginning, this was also done by Winternitz, but Winternitz had a couple of problems. Was focused on a couple of ideas, very good ideas, but there is no general formalism for this stuff. They only have applications for certain interesting, physically motivated problems. Yeah. Well, you can define a system in dimensional manifolds. I did interesting things. Yeah, there are technicalities. There are Lie systems related to infinite dimensional Lie algebras. Yeah, it is possible. At the beginning, I said that they are finite dimensional. They are infinite dimensional ones, given superposition rules. If you have that on an open neighborhood of each point, the original Lie algebra reduced to a finite dimensional one. So it's that kind of technical stuff. You can start making claims about that. The fertile theorems are not absolutely true if you are not careful. You can deal with infinite dimensional Vessiot Lie algebras that they are extension of finite dimensional ones. For example, how was this? I don't remember exactly. I don't remember the name. Sorry. Okay, let us say this. Under certain conditions, you can generalize the idea for Lie systems, for systems that have infinite dimensional Vessiot Lie algebras. Yep. And there are more stuff. It turns out that we found lately that Lie groupoids and Lie algebroids are useful to describe certain technicalities about superposition rules that previously, for example, that they are locally fundamental and things like that. So now we are working on it. So it's something that we are also trying to study. We are also trying to give a categorical approach to the systems. Wow. This is more or less what we have been done. My ideas, what I've done, yes, to sum up, is that from 2001 till 2009, I did my PhD on Lie systems and certain generalizations, okay, quantum mechanics with certain technical assumptions. In 2009, I noticed that we can mix these things with geometric structures. There appears the Poisson coalgebra methods and things like that, relation with certain geometric stuff. After a certain time, we found K-simplectic Lie systems, and we found how techniques for field theory could be used to study Lie systems. And in 2019, 2025, we started studying multisymplectic systems. And I started studying systems, differential equations that they are not differential equations in the usual meaning. I mean, they are stochastic, they are discrete, or they are defined on a specific manifold. For example, I was studying the manifolds, yeah? And we are working on this, yeah? I've worked with this with Carinena, Campoamor, Grabowski, Herranz, Winternitz. Well, we talk about it, we never publish anything that is Sardon, of course, Villarinho, with Grundland, with Rivas, with Sobchak, many others that is difficult now to put them out. So the thing is that Lie systems is a good thing to study integrable system, control theory, classical quantum field theory, and provides a bridge between pure and applied differential geometry. So for me nowadays, Lie system is a good thing to study differential geometry. Yeah, it gives hints. At the beginning, I used differential geometry to study Lie systems. Now it was the other way around. It's more or less what I think. But in any case, it's a nice bridge between differential geometry, between algebraic techniques, and integrable systems. So I think that this is the end of this talk, but the theory of Lie systems continues. Yeah, after 16 years, there are more young people working on the topic, developing new things. Even if some people working on it passed by, like Winternitz and all of it, but one time passed by, decided that they want to study another topics. It turned out, to my surprise, that young people, PhDs, wants to keep on working on it, and the story continues. I hope it will be so for many years. So thank you very much for your attention, and thank you very much for those who work with me for continuing this topic, because I had a lot of fun with it and with you. Thank you.
Thank you very much, Javi, for very nice, very interesting talk and very deep historic overview on Lie systems. And are there any questions, remarks?
Yeah, hey, Javi.
Oh, hi.
Hey, this is Mark. How you doing?
Fine. Indeed, I have to talk to you.
Hey, I got a question for you. If you could just slide back to the PDE case.
Yeah, sure.
You probably knew I was going to head that way, right?
I didn't saw you. I just noticed you now. I could say something about it too. Come on. Okay.
Let's see. Yeah, let me think about this here for a second.
Yeah, sure.
Yeah, because see, so of course, Vessiot was definitely interested in the PDE case.
Yeah.
And it actually is a fair bit different than the one that you've listed here.
Yeah.
And he was definitely interested in generalizing the scalar case.
Mm-hmm.
But in a different direction than this is.
Mm-hmm. In the direction of your work, I guess.
Correct. Yes.
Okay, because I wanted to talk to you for the moment. But yeah,
what's that?
Yeah, no, tell me. Go on, please.
Yeah, but it's a little hard to describe in any small amount, like verbally. But there's a pretty good description. Oh, sorry.
Sorry. Please go on.
Yeah, I'm trying to think of how I could write something down here meaningful, but I should. I haven't done it to prepare for right this minute, but I think if I was going to, there's a good description of the difference of what you have here, and in Stormark's book on how it compares to this what you've written here. So it's hard for me without writing something on the board.
Okay,
but it's more like let me think about this. I'm trying to let me try. I just threw out a message here. I'm willing to talk about it, but I don't know if I can explain to you right at this moment the difference in what you've written. I'm trying to think about it here. Yeah. I should probably just give you a little talk on it. It's it's closely related, but it's he definitely went in a different direction of generalizing the PD version than what has been written there. But it is definitely a generalization of Lie systems to PDEs, but in a different direction.
Mark, there is one thing I wanted to tell you. It would be very nice if we could talk next week, for example. Quietly, we can prepare what we have. We can talk to each other and think a little bit about what we had in common, because it could be nice to start. So Thomas read your works and took more time than we thought, but we can comment on it. Yeah.
But hey, let me give you an example that might clarify things, right?
Yeah.
So that the Riccati equation, you can define a curve into SL2R, and then quotient it down to the reals to pick up the Riccati equation.
Yeah, sure.
A curve into the Lie algebra. You take a curve into the Lie algebra, project it down onto projective space, and then you get the Riccati equation, right?
Yeah.
Okay.
Sure.
So you can do the exact same thing with, say, a function from C into SL to C. Just change everything from T to
the complex number.
Yeah, no problem. And it looks exactly the same.
It's like a holomorphic version of the thing. Yeah.
Yes. Yeah. However, here's where things change. So in that case, you're going to take SL2C or SL2R, it doesn't really matter. And it's quotiented by the, let's see, is it the upper triangular? Let me remember. Yeah, I think it's upper triangular, right?
Yeah.
Right. So that gives you the line, that gives you the line, and it gives you the Lie system on the line. Just as we all know, and it's Riccati. Okay.
Yeah.
Change that group in the complex case to SU2.
Okay.
And things get really strange. And that's what Vessiot was looking at. It doesn't look anything like what you think of as a standard Lie system, like just a single ODE, like Riccati.
Well, I confess I didn't think of that, but it's quite natural from what they thought.
Yeah, and so that's exactly what happens. And so that becomes then an elliptic partial differential equation in the plane now, and not, I mean, it's still an equation of Lie type, but it has a way different flavor than, say, Riccati.
Yeah, let me tell you that, I mean, parameterizing by the complex number is something that indeed we were thinking with Thomas. But the thing you said with PDs, wow, I didn't think of it. Really speaking, it's I have to take a look.
No problem. And I just sent you a message. Like I wouldn't mind talking about that stuff, and I could give some examples, and then it might be more clear how it's similar to equations of Lie type for PDEs, but it has some differences as well.
Yeah.
And it's it's hard to do just like in this situation without something being written down. Drawing the analogy to what you're talking about.
Yeah. And this is
up to you. If you want.
Looks interesting. But as I said, it would be nice. Well, okay, I would say an email, okay, this evening. And we can fix a date if you want. Next week, for example. And we can talk about it quietly and start thinking about it, because it's something I'm interested in this. One of the things I didn't say is about your work, because it's another way of
So I think here's another way to think about it, right? Like if you have just even a scalar ODE, you can find for the right-hand side necessary and sufficient conditions that it's an equation of Lie type, right? So that the right-hand side sort of factors in this curious way. Okay. And so, what Ian and I did was a very similar thing, but for partial differential equations, which have this sort of Lie type behavior, but it's a bit different than the type you wrote down. And that's what Darboux integrability is it allows you to determine sort of this Lie algebra decomposition of the partial differential equation. But it's, again, a little bit different than the Lie type you wrote down on those notes.
Yeah, and indeed, is something I wanted to tell you about. In short, I was discussing the topic, for example, with Oscar, and it turned around that your approach, we could retrieve Lie systems in a particular type, but it turned out to us, what we found is that, and we wanted to tell you, that they are both different things. I mean, we couldn't retrieve every Lie system in the way you did, but there were some cases that were able to be described. So it turned out that it was to our surprise. We have not hard proof. I mean, we have to check what we have, But instead, we wanted to discuss it because it makes your idea much interesting. It's more different than we thought at the beginning. What you said, it would be nice to think.
Okay.
So thank you. I would say an email.
No problem. Sorry to drag that out for people.
No. It's the seminar is for that. And it's a pleasure to have fun and to discuss, actually.
Yeah.
That's why.
Yeah, well, as you were talking about it, I'm like, oh man, I should really just kind of like draw the analogies and sort of compare it to a little bit of what Vessiot had been doing when he kind of branched off from Lie's approach and how it was related to Darboux and stuff. But in some ways, what you could be thinking about is what we're able to do is figure out that sort of right-hand decomposition, but in a PDE setting.
Yeah.
And that this weird thing of Darboux integrability detects this, and that, then there's this algorithm to break apart the right-hand side. But it's in a little different way, but it is similar to that.
Yeah, I mean, the interesting part of the thing, Mark, is that my feeling is that many things in the Lie system theory so far with these ideas, they're a little bit too much studied. I mean, that's it's difficult to find anything else. New ideas similar to be developed, they are very, very well.
Right. But the Vessiot's approach is definitely different.
Yeah, indeed, I got convinced taking a look at your papers after a while. I mean, I thought I was more similar.
Right.
But no,
it's not.
No,
it's not.
No,
but it is a generalization for sure. And I sat down. I could definitely kind of draw the analogy of what he did and how he was how he got to that from the Lie systems, the standard form of Lie systems for ODEs.
Okay, so we can definitely later.
Yeah. I mean, when Ian talked about it, he didn't quite approach it that way, but
it's fun. Indeed.
Yeah. Anyway, all right, man. Well, sorry to drag that out for you.
No, thank you. It's very welcome. And okay, so I don't know.
Get back in touch and we can talk and continue on.
Sure.
I would prepare for something formally. I was just sitting here this morning and then I saw the email. Oh yeah, there's a thing going on. I'm like, I jumped on it to see what was going on.
I didn't expect you, but it was nice to see you. One thing, Mark, have you talked about, do you have any talks or you have been working on this or saying something somewhere? Because, I don't know if you have been giving some talks about this proposition somewhere or something, or you have been.
Well, I mean, Ian spoke there, but I think we have never really given many talks on its relationship to equations of Lie type and systems of Lie type and how it compares to that. I gave a talk once, like a few years ago, about that. But, we haven't really done much on that, I would say.
Okay.
Like a direct, and that's why I threw it out. I just sent you an email saying, "Hey, I can do that if you would like to see it," and it would make things a little clearer what the difference, what the similarity is that Vessiot was looking at, or the generalization, I should say, that Vessiot was looking at to these systems. So, but they're very closely related, or a very close, comparison to these things. Anyway, we can talk about it.
Yeah, sure. Okay, so
are there many questions? Are there more questions?
Yes, maybe if I can.
Yeah, sure. Yeah.
Hi.
Thanks for coming. We don't see you, but
yes, I'm seen or not. Well,
very
something wrong. Maybe
dark.
No, never mind.
So tell me.
I have two questions.
Yeah, sure.
Maybe quite simple. One is. Decio Levy and Pavel Winternitz wrote a series of papers on discretization which preserve all Lie point symmetries.
Yeah, I remember that.
This line, is this approach, research was along this Lie systems line or something different?
I will tell you the truth. I'm not sure because it's been something that I just took a look lately.
Yes,
what the idea is that they discretize the system in such a way that the symmetries of the list system, they are kept. Okay, there's some kind of discretization that satisfies this. So it wasn't, as much as I understood, it wasn't about all symmetries. Yeah,
maybe not all, because there are problems in discrete case, of course.
Yeah.
Well, never mind. I thought that maybe it is, in a sense, well known to you.
Well, it's no,
and,
truly.
And another question, quite simple, but I wonder what is the answer. In this simplest possible case, so ODEs with constant coefficients,
yeah,
linear and linear. We have this structure as a combination of exponential functions. So is it a very special case of this Lie system?
Yeah, it's a very, I mean, the coefficients are constant, you related to a group as before, but the thing is that in the Lie group, the equation is autonomous. So it's one vector, so you make the exponential, and
exactly.
The thing is that.
And because what is for me now, at least since several years, interesting is usually discretization or this discrete case. And in this simple, maybe trivial case, probably any one-step numerical scheme has the same properties that it can be combined. Solution can be written as a combination of some discrete exponentials.
Yeah, this is some of the ideas you find. This is the thing that it's Piotrowski who did it. Yeah,
who?
Gabriel Piotrowski was a student. They have some of the ideas that were about this. That you have certain simplifications about these methods. Well, there are things we did with Cristina Sardon, Fernando Jimenez, and a student indeed, and it was. Instead on the manifold you put the problem you relate it to a problem in a Lie group, yeah, and you make some numerical discrete methods on the Lie group. Yeah?
Yes, of course.
Yeah,
Because from the point of view of calculations or this discretization, it looks rather not so difficult or easy.
Yeah,
but
this was the idea.
Good. Maybe good toy model to see how this Lie structure works. For me, it would be nice. So there are some papers.
Yeah, there are some papers. As I told you, there is one paper by Cristina, Fernando, myself, Alfonso.
Never mind. Maybe you can
find
send
it.
me.
I can send you. Yeah, I will send you.
But anyway, it is highly non-unique, of course, probably.
Yeah, no, of course. The problem we had is that we expect to find anything, yeah? And you have several ideas. You have the works by Pavel, who said even in which sense you will have an integrability of these systems. He started doing how this has to be done. But as I said, there is no theorem, there is no formalist, there is no general idea. You have just intuition about it. So if you ask me how to do it, I will tell you that I have no idea. I mean, it's something to work on.
I asked you, is there in this particular case this map, this structure? Because it could give some some point to think about this the structures and this system and so on. No, but anyway, I'm glad that it is related in a sense.
Yeah, Ian, I will send you the papers and I will tell you something. This is one of the interesting things I had to solve, but I wasn't able to do so far. I mean, so what you are pointing out is something that it was a certain moment important to us. So it would be nice to discuss if you have any problem. Yeah, it would be nice.
Maybe we can meet during the next November seminar of Maciej niż Polsku.
Yeah, sure.
Because there will be a meeting in November. It is not clear when, but certainly in Wednesday.
Yeah, so it's Wednesday. Wednesday is not, but I have a lot of teaching, but I have time. So it would be. I will have time to talk. Yeah, we will meet. We can talk, discuss quietly, and see what is going on. As I tell you, it's something that is open to me. I thought about it for a while, but I'm not either an expert on discrete methods. I managed to do a couple of
vice
things.
Vice versa, so I'm not expert not at all in these systems, in these structures, but I feel much better in the field of numerics.
We can have each other. So,
thank you.
Thank you. Yeah.
Thank you.
Okay, so maybe last short question. Okay, so maybe I'll ask, could you provide an example where the Vessiot-Guldberg Lie algebra is infinite dimensional?
And you have a superposition rule? Yes, of course. There is a tricky one, okay? Very stupid. The thing is, you can put on the real line a set of vector fields. They will be smooth but not analytic, yeah? And they will be done in such a manner that for example, there's one will be a bound function, the coefficient on partial on x, a bound function from 0 to 1, yeah? Another one would be a bound function between 1 and 2. The second, the third, the following one, 3 and 4, and so on and so on. Now give a time-dependent vector field which is a linear combination of all of them together, yeah? So it is an infinitely dimensional Lie algebra, but you have a superposition rule, and the trick is locally at a neighborhood of its point, then you can put at this as small, then you will have an open where the Lie algebra is, for example, R2. Yeah, it is abelian, and in that point you will have a superposition rule. This is the one thing. So it's not true that a Lie system is always related to an infinite dimensional one. The real statement is that locally, the Lie algebra, the restriction of the Lie algebra to an open enough small open neighborhood of a point, it has to be infinite dimensional. This is the first thing you say about the theorem that they are not true. The second thing you are telling is that there is a result by Lie saying that every Lie algebra, infinite dimensional Lie algebra of vectors is on the real line is locally isomorphic to a Lie subalgebra of SL2R. But the example I gave you close to a point is not true because these are two, and SL2 has no abelian subalgebra. So this is not true also, because the trick is that Lie was talking about analytic vector fields. All the whole theory is always about analytic vector fields. If you change the category to smooth ones, it turns out that there are many more examples. This also goes to the classification by Lie and certain classification of vector fields, because there are smooth problems that they are interesting, and they are not classified by Guldberg, they are not classified by Artemio. And it was fun because I talked to Winternitz many times about this classification, and he told me many times it's not complete. He was always saying, I said, oh, give me a counter example. I will think of it. Just one day. He never told me that. At the very end, I buy myself for that is not complete, because with small vector fields, they are counterexamples. They are examples that are not related. They are related to stability problems, and they are interesting, and they are not contained in this stuff. But it's much more complicated than this. So many of the results that are written, they are true, but you have to put the technical conditions properly, because if you don't, they are not anymore true. And you can miss certain important examples like this, okay? But once again, I never wrote it. Never did it. It's something that I can tell you, you can write it if you want, at the moment you want. For me, it doesn't matter. But it's like that. It's a curiosity, and I hope it can be relevant. Thank you.
Okay. Thank you very much. And thank you all for attending. Next week, our guest will be Professor Jan Cieśliński, who will talk about application of Clifford algebras and spin groups to integrable systems. So see you in a week.
Thank you, Jan. Thank you, everybody. And see you.